Hello, the following video is a recording from our third astrophotography workshop taught by Mustafa Aydin and held in MetaJungle Discord. This session was held live on January 20th, and this class is the beginning of our Deep Space Astrophotography. So in this session, we're going to cover the equipment needed. So that's going to cover your telescopes, mounts, tracking devices, cameras, and software. This class was very informative, and so we hope that you find it useful. The goal with MetaJungle is to create tools and resources to help empower success. We hope that you like, share, and subscribe this video, and join us in MetaJungle Discord.
Today, it's going to be an introduction to deep space astrophotography. We will mostly be talking about equipment. And let's go. So what is deep sky astrophotography, or what is the subject of deep sky astrophotography is? Of course, nebulae and emission nebulae, which are actually hydrogen. The first element on universe was hydrogen, and most abundant still element is hydrogen in the universe. It has one electron, one proton, and one neutron, and it is the basic and also the lightest element in universe. So if these hydrogen atoms are provoked by some kind of energy, and most of the time this energy comes from the young energetic stars, the UV light will stimulate the hydrogen atoms, and they will glow in red. And when this happens, it's called emission nebula, because they emit light, and it is in red color. It's 656 nanometers. So that's why they are called emission nebula, and they are most of the time reddish, have reddish colors. And the second one is reflection nebulae. Besides gas and things, there are lots of other gases and material like dust and some material all over the universe. And when the star is not energetic enough to create emission nebula, they create reflection nebula, because this material or gases there glows with the they actually reflect the light from the nearby star, and these kind of nebulae are called reflection nebulae. And this is actually a new, fairly new concept called integrated flux nebulae. This says, there is lots of matter, let's say within the Milkyway galaxy, our Milkyway galaxy, and this material, this gas and dust, is illuminated by the integrated light of the stars from the galaxy. So, total light of the coming from the stars are illuminating the material within the galaxy, and these are called this is called integrated flux nebulae, and it is very, very faint, and it is hard to capture, or you have to shoot very long integration times. Like I have one photo that I have a total nearly 40 hours of integration time. So you will see it as a very faint dust and gas in your photos. So, and of course we have galaxies. For instance, I received a question last week. Someone was asking how we can shoot our galaxy as we are inside it. So the answer was we can shoot our galaxy, but we cannot shoot our galaxy as we are shooting Andromeda galaxy or other galaxies, because we are not able to look at our galaxy from outside, because just imagine the oldest spacecraft launched by human has just left solar system, let alone galaxy, our galaxy. So what we see when we shoot our galaxy is one of the arms, inner arms, because we are in an outer arm in the galaxy. We just shoot a photo of one arm. But of course, there are lots of galaxies other than our galaxies, and this was actually discovered by Hubble, Edwin Hubble. He discovered that Andromeda galaxy was actually a galaxy like ours, and then they started, as the telescope started getting more powerful, they started finding out lots and lots of galaxies. So also galaxies are subject to deep sky astrophotography. We have star clusters, and star clusters are actually two types. One of them is open star clusters. The best example to this one is Pleiades or Seven Sisters. It is one of the nearest open star cluster to us. So it can be seen naked eye. And these star clusters are most of the time stars which were created from the same media, same hydrogen gas. When they are born, they are bound to each other with gravity. So for some couple of hundreds of millions of years, they stay together and then they separate. So it is also guessed the same thing for Pleiades. They are now around. They are very young stars, actually, around 100 million years old, and finally they will separate from each other. And globular star clusters are like thousands of, sometimes 10,000s of, sometimes 100,000s of stars are together as a ball, as a globe. So that's why they are called globular star clusters. And the latest studies show that globular star clusters are actually the oldest things in our galaxy, and most of them are located in a part called Galaxy's Hollow. And for now, there are like a little bit over 100. But it is thought to be there are more. And last, we can say that that they are deep sky objects, but they are actually not deep sky objects. They are from our solar system. There are actually two types of comets. One is short period comets, and the other one is long period comets. For instance, the one that visited last year, the comet Neowise, was a long-term, long period comet, which is thought to be coming from an imaginary or hypothetical region called Oort cloud. It is thought to be there's a cloud. There are thousands, maybe millions of comets there, and from time to time, comets come inside the solar system. And the second comet type is short period comets, and these are coming from actually a place called Kuiper belt, which is right after the planet Pluto. It is also thought to be there are thousands of millions of comets from residual from the first days of our solar system. So these are the subject to deep sky astrophotography. And as we said, today we will be focusing on equipment. First of all, we need an optical device, which can be a camera lens or a telescope, as it seems in this picture. This is my equipment, by the way. So this is my telescope, and I will tell you the details. And then we need a mount or tracking device. Here, this piece is called equatorial mount or the tracking device. And auto-guiding system, this red thing here and this black thing here is actually another telescope and another camera pointed towards the same direction where your telescope is looking at, and it helps tracking. It helps to have more accurate tracking, and we will be explaining. And of course, we will need camera and filters. Filters are not like must for at least color cameras, but for mono cameras, of course, we have to use filters. And of course, a computer, some accessories like cables, spare cables, power supply. This thing here called, it is used for polar alignment, the counterweight, dew heaters, and lots of other stuff. Some connection adapters and stuff like that. And of course, power supply. In the coming slides, I will not be explaining this, but this device and other things needs actually electricity, of course. If you are, for instance, this one, I was in a hotel, which is where it was far from cities, so it had some nice skies without light pollution. So I had landline electricity. But if you don't have, and if you want to go somewhere remote, for that I use a gel battery and also solar panels to recharge the battery. And power supply is crucial, of course. Okay, so let's talk about optical device. As we said, we need lenses or telelenses. I want to say lenses and telelenses because there is a misconception that everything in the night sky, those galaxies or nebulae or those star clusters are so small, and you need lots of magnification, which means you need lenses or telescope with really high focal lengths. But that is not true. There are some deep sky objects that are really big. For instance, if we talk about Andromeda Galaxy, Andromeda Galaxy is actually as big as 6 full moons in the sky. I mean, 6 full moons. Just put 6 full moons side by side. It is that big, but it is so small. It is so faint that you cannot see it as you can see the moon. But it is that big. So that means that you don't actually need very high focal lengths and very big magnifications. For instance, this lens here is 135 millimeter. I have one of these lenses, and it is a phenomenal lens. And I shoot lots of galaxies, not lots of galaxies, few galaxies, but lots of nebulae with this lens. So it means that you don't need to necessarily have high focal lengths. For instance, I have friends that they are shooting with 35 millimeters, 50 millimeters, 100 millimeters, 85 millimeters focal length lenses. They shoot some awesome astrophotography. So let's break this misexception that you need a big telescope or you need high focal lengths. And I have one threshold here. If the lens is more expensive than a couple of $100, then you have to go to telescopes. I mean, I would never buy a lens for, let's say, over $500, because at that time you can go and buy a telescope with that money. So for deep sky astrophotography, I wouldn't spend, let's say, more than $500 for a lens. And telescopes, there are actually mainly, and for the ones who are more curious about lenses, I want to refer to our first class, and I talked about lenses quite long in that class, so they can go and find how they will choose or pick a lens for astrophotography. And we have telescopes. Actually, telescopes are not different than lenses. We have two main types of telescopes, and there is the third type. The first type is refractor telescopes. Refractor telescopes has a glass in front and some other glasses to create the vision, and they are called refractor or Galileoscope or Galilean telescope because we will just talk about Galileo. He was the first to use refractor telescope to look at the heavens. So the second type is called reflector telescopes. Reflector telescopes, instead of having a glass, they have a mirror on the backside here, and they have another mirror here. It's called the primary and the secondary mirrors, to discard some of the disadvantages coming from refractor telescopes that we will be talking about in details in a minute. And the third type, they are called catadioptric telescopes. They're actually, hybrid telescopes of the first two. They have glass here, and also they have a mirror, and they have the secondary mirror. And these telescopes are have advantages and disadvantages we will be talking about. So it is the mix of the first two. And let's start with refractor telescopes. Like I said, they are called refractor or Galilean telescopes or Galileoscope. As you may know, Galileo was the first person. He didn't invent the telescope. Actually, it was invented by a Dutch guy to use in military purposes. But then Galileo thought of using it, looking at night sky, and he studied moon, and he studied also the planets, which are the brightest ones, like Jupiter, and he made these drawings. For instance, these are his drawings from the moon. He looked at the craters. Some regions in moons are called mare, so it means actually sea. He thought he was seeing seas on the moon, and of course he saw the craters and everything. He made these drawings, and he also observed Jupiter mostly. And he here you see actually Jupiter and the biggest and the most bright for moons of Jupiter. And he realized that these objects were actually revolving around the planet. And by that way, he understood that those were the moons. And those moons are called Galilean moons. And those moons are Io, Europa, Ganymede, and Callisto. And actually, Ganymede is the largest moon in solar system. So he discovered these stuff, and of course, he discovered lots of more stuff. And let's have a look at the refractor telescope anatomy. So, like I said, there is a glass here, and light comes from front, and it is scattered by the objective lens, and by using another lens called eyepiece lens, you can either reflect this vision to your eye or a camera. So it is this as basic as this. Even the most modern telescopes are the same, have this technology. The only technology is changing is the quality of the glass and the coatings that glasses use. Other than that, it is the same since Galileo time. And it has pros and cons. Let's have a look at the pros. They have impressive contrast and sharpness if, of course, they are manufactured, in a high-end level. There are some telescopes that are, stunningly awesome, and they are easy to use, and they are light, and they're not heavy, and they are easily transportable. They almost need any maintenance. They don't need any maintenance. Maybe from time to time you can just dust it off, but we try not to touch the objective lens or try to clean, just not to ruin the coatings. And they have closed tube system, so there will not be any dust or other outside world things will be going inside your tube and dirtying your telescope. And the cons are as they are made of glass, and I should say that the size really matters in astronomy and astrophotography. The larger the lens or larger the telescope, it is better. So if you want to go for larger telescopes with refractory style, after a while, that glass cannot even carry itself because glass is an material, it will bend itself after a while. And of course, they will be extremely heavy and they will be extremely expensive. That is why you cannot go above certain diameter in refractor telescopes. And because the light is going through a media, we talked about this in our first class. They create chromatic aberrations because once the light enters to the glass media, different wavelengths of lights move at different speeds within the glass. And then this will cause chromatic aberrations or color fringes, and especially around the stars, and which is something that we don't want. Of course, there is ways to avoid chromatic aberrations. You can just coat the glasses with different coatings, which are called ED, extra low dispersion coatings, or you can make achromatic telescopes, but these will also increase the price of your telescope. And again, the higher price, and then we have the reflector telescopes, or called Newtonian telescopes. Newton, as you know, he was a very big physicist and also mathematician, because he invented calculus, and he discovered lots of things, and he is also the owner of classical mechanics and laws of motion. Of course, he worked on optics also, and he created his own telescope. Instead of using glass lens objective, he used mirrors, a concave mirror, to create, to collect light and create vision from the mirror. So this is the intersection of a reflector or Newtonian telescope. Here we have the primary mirror. The light coming from celestial body comes from here, and it is collected by the primary mirror. And then there is another mirror called, there is a secondary mirror, and then we have the eyepiece to create the vision coming from primary and reflecting through secondary mirror. And these are called reflector or Newtonian telescopes. Yes. And reflector telescopes have also pros and cons. They have higher apertures, and the same aperture, the same diameter of refractor telescope and reflector telescope. Of course, the reflector telescope will be much cheaper, and will also be higher aperture, which means fast optics. This means that you will have somewhere between f3 to 7. They will have higher capability of collecting lights, and they will be, of course, cheaper than the refractor ones, and they can be made even bigger. For instance, the Hubble Space Telescope is a reflector telescope, actually, and the James Webb Telescope, which has over 8 meters of mirror, and it is again a reflector telescope, and the biggest telescopes located on Earth, especially in Chile or Hawaii, Keck telescope, they are reflector telescopes. So it is easier to make larger with a lower price. And as the light doesn't go through a media, they don't create chromatic aberrations, which is absolutely beautiful feature. And sometimes, if they're not manufactured high-end quality, they can have low optical quality, and then you may have to use other devices or accessories to fix this low optical quality, or you may need to go and buy a better telescope. And they need periodic maintenance, some maintenance called collimation, because they have mirrors. It has a reflector telescope has two mirrors. These two mirrors has to be aligned to each other very carefully to be able to have good vision from the telescope. And this collimation can go bad even when you are carrying your telescope. So it needs periodic maintenance, and it also needs mirror cleanings, which can be tricky and tedious. And they are open tubes that here, as you can see, this front side of the telescope is open. So it is totally open to air. So lots of things. For instance, I have friends that spiders went inside and lived there in their telescope. So that can be a little tricky to clean those things because they are open tube systems. And they are bulky and heavy, so it is not easy to store or carry. And there is another cons for reflector telescopes. And as they have a secondary mirror in front of the primary mirror, this mirror cuts off the light a little, and this causes loss of light, and the whole diameter of the primary mirror cannot be used efficiently. And as they have open tubes, they are open to dust, humidity, and also other stuff. And the third one is catadioptric telescopes. Like I said, it is actually hybrid telescope, and they are relatively new designs, and they have different designs called, for instance, Max-Stov Cassegrain, Schmidt-Cassegrain, Argonov Cassegrain, and so on. These are the surnames of the guys that developed these telescopes. So there's some little changes in the telescopes, but they're actually the same. So they have this is the front side. As you remember, in the Newtonian or reflector telescopes, there's nothing here, but in this type of telescopes, there is a corrector glass here. The light coming from the celestial object is corrected by the glass, and then they go hit the primary mirror, and then they go, there is a secondary mirror here, and then they reflect from the secondary mirror, and then they go to eyepiece. So for these telescopes, like they are usually very short tubes, and they can have very high focal lengths because the light moves within the telescope 3 times. This is the first one, second, and third. So let's say if this tube is 30 centimeter, its focal length will be 90 centimeter, which is amazing. You can have a very small telescope, 30 centimeter long, but has a 90 centimeter or 9,000 millimeter focal length. So this combines, cathodioptric telescopes combines the advantages of mirror or reflector telescopes and the refractor telescopes. So they are like they have more cons. They have more pros than cons. And let's see, they are also closed tube systems, so no dust or humidity or spiders will go inside. And they are compact and very light comparing to refractor telescopes. As they're compact and lighter, they're easy to handle, easy to carry, and they don't need much maintenance. They also need collimation, aligning the two mirrors, but not as much as reflector ones. And like I said, they combine pros of two types, and they are greater than the two other types. And they almost have no chromatic aberration, which is very big advantage. And cones, they are a bit more expensive than the reflector ones. And they, again, need some periodic maintenance, but not as much as reflector ones. Again, here, because of the secondary mirror, there is some loss of light. And let's have a look. Maybe we can, I should ask, are there any questions so far? I don't know. Anybody has any question? Looks like no questions. Okay. And sorry. So we have in telescopes, there are two parameters that are really important. The first one is focal length. Actually, focal length is a distance, and they are given in millimeters. Actually, between the telescope's primary lens or mirror and the point where the lights come together in focus. You see, so the focal length here, the distance between the primary objective lens and the point where the light rays come together in focus. So this is called focal length. And this is an important parameter because by using this parameter, we will calculate the F ratio that we also mentioned and talked about in our first class when we were talking about lenses. And the other parameter is aperture. This is the physical aperture. We can use this analogy, actually. We can think that telescopes are actually buckets that are collecting light. So the larger the bucket diameter, they can collect more lights. Imagine if you had two buckets. Let's say one of them has 10 centimeter of diameter, and the second one has 20 centimeter. And when you put that bucket under the rain, of course, the 20 centimeter bucket will collect more water from the rain. It is the same for telescopes. The larger the aperture, like I said, in astronomy and astrophotography, the size matters. Like the bigger the telescope is, the better. So when we have higher aperture, that means that we will be able to collect more light in a given time. And using this focal length and aperture, if you will remember, we will calculate F ratio. F ratio is also known as aperture, and it is division of focal length to physical aperture. It will give us the F ratio. This is a very good example. See these pipes here. This is F8. It is longer. It is actually twice as longer, like this one, and has the same diameter. So this telescope, or this lens here, let's say this telescope, will have F8, and this will show one thing, and I will explain in a minute. And as you can see, this is half as this one, and this will have another thing. Let's see. We have a term called FOV, which is actually field of view. Imagine looking through this one. You're looking at it. Let's say you're looking at a tree. You will see a smaller portion of the tree comparing to looking with this one, because this has a smaller field of view comparing to this one. And let's see here. For instance, this is Andromeda galaxy. Remember, this is 6 full moon large. And this is my telescopes and cameras features. It is 1.5x crop. So this is the size of the sensor actually. And it has 350 millimeters of focal length, and its diameter is, I actually forgot to write the diameter. Its diameter is 70 millimeter. So it will make F5. And you see the Andromeda galaxy just fits to the FOV, the field of view. This red rectangular is my FOV, field of view. So when I use my telescope with a 1.5x crop sensor, I will have this big field of view. So this is like the angular size of the sky. It is nearly 4 degrees to 2.3 degrees. And let's have a look with some other optic, which is again on 1.5x crop sensor. And this time it is 135 millimeter focal length, and it is F2. Can you see the difference? This is our field of view this time. It is almost 3 times of the previous one. So you can see almost 10 degrees, this long side of the rectangle. So it was almost 3, 4. So the Andromeda galaxy was just fitting inside the field of view. And when we have a faster lens with F2, it has wider field of view. So knowing that, when you're deciding what equipment you're going to buy, you have to know what kind of field of view you will have. So if you want to buy a lens like this, you will only be able to shoot one or two galaxies, because the galaxies are smaller, and you will be able to shoot lots of nebulae. So when you're buying an gear, a telescope, you have to calculate your field of view, and you can do that. This is actually the Stellarium program that we talked about last week. You can calculate your field of view by Stellarium program. You will see what is your field of view going to be. And if you want to go for galaxies, if you love galaxies, and if you want to shoot galaxies, you shouldn't be buying this lens as optics, because you will only be shooting, I can say, not more than 5 galaxies. You will be shooting a nebulae instead. I really hope that it is clear. And I don't know if we have questions. I can take questions till now. I think there is no questions again. Okay.
Actually, we do have one question.
Oh, good.
It's so do you want to calculate the field of view before you purchase a telescope to ensure you get the one you want?
Yes, absolutely. Because most of the time the ultimate questions I always face, and my friends always has, is what telescope I should buy. And most of the time, if there is no more information in this question, my answer will be another question, because first of all, I will ask for the budget, and then I will ask for the purpose. Like I said, if you want to shoot galaxies, then you need a higher focal length and higher F ratio, so that you can have a narrower field of view. That's why if you want to go for galaxies, then you need to buy higher focal length telescope. But there's also one thing that is always asked. I want to do galaxies, I want to do nebulae, I want to do planets, I want to do sun, I want to do everything. You cannot do everything with one optics and with one camera. So different types of astrophotography needs different types of telescopes and different cameras. So most of the time, if the astrophotographer is interested, let's say, in deep sky astrophotography, also planetary astrophotography, then they will have to buy more than one telescope. That is why this thing is really expensive. Okay, I think this answered the question. And the second important piece of equipment is they are called mounts, or we can say tracking devices. These have different types again. One of them is called alt azimuth mounts, and the second one is equatorial mounts. When you're picking a mount, you have to think about payload capacity. Again, before buying your mount or tracking device, you will have to know what telescope or telescopes you will have, and what other equipments you will have, and what is going to be the weight of these equipments. Because when you're deciding on your mount, you will have to know the payload capacity of the mount. I mean, the mount will come when you're buying a mount. You will decide by its payload capacity and the drive types. There are some different types of drives. This actually shows how the movement from the motors is transferred to the other moving parts. It is called drives. So you can buy geared ones. These are the most common ones and the cheapest ones. There is other types called direct drives, friction drives, etc. And direct drives and friction drives are the more expensive ones. And also, you have to decide, are you going to use a manual one or a computerized or go-to one? Manual mounts are generally used for smaller equipment, like one DSLR camera and one telelens, that you can point your camera and lens to the object that you want to shoot. Because once the telescope and other stuffs get bigger, the focal length gets bigger, it is almost impossible to find where your telescope is pointed at. For instance, with big focal length telescopes, it is even hard to find the moon. Imagine moon, it is moon. I mean, it's the biggest thing after the sun, the biggest thing we see in the night sky. So it is even sometimes hard to find the moon when the focal length is high. So if you are looking for small galaxies or small nebulae, it's almost impossible without computerized go-to mounts. And the first type is alt-azimuth mounts. These mounts are actually working on X and Y axis. You know, it goes up and down, and it moves left and right. And these type of mounts are best used for visual observations rather than astrophotography. Especially there is one type called Dobsonian telescopes. These are the best for visual observations. But still, if you want to use this type of mounts for astrophotography, it is better used for planetary astrophotography, because with planetary astrophotography, you will not need long exposures. As the objects are really bright, you will need very, very short exposures. Actually, not even exposures. We shoot short videos, and then we pick the frames from the videos which are the best. So that is why you don't need high quality tracking, and these alt-azimuth mounts will also cause something called field rotation mistake, because when you see here the Orion constellation, when Orion constellation starts rising, it will be almost parallel to the horizon, and it will go like this. It will change the orientation, and this type of mounts cannot track that orientation change. At the end of the night, you will have to cut lots of information from your photos to be able to align the photos. And another thing here, the plane that your telescope is on is parallel to the horizon plane. So that's why they are called alt azimuth mounts. And they are not good for astrophotography. They are good for visual observations. And if you have to use, you can only use for short exposures and also for planetary astrophotography. And the second one is called equatorial mounts. That is what we use. Remember my own equipment, it looks like this. It is an equatorial mount. For this mount, the plane that telescope is on is parallel to the rotation axis of Earth. So if you see here, this is the South Pole, this is the North Pole. So this the Earth rotates around this axis. So the plane that telescope sits is parallel to that axis. And it has three axes. One is called polar axis. This polar axis must be facing Polaris, the North Star. And it has also right ascension and declination axes. And they are computerized and motorized. You can say this mount go to Andromeda galaxy, and when your telescope is on, it will go to Andromeda galaxy and find. Because this telescope, when you start configuring it, this telescope will know where it is on Earth, what physical location, and we will make some adjustments to so that the equatorial mount will know where it is on Earth and will easily find the night sky objects using its computer. And this type of telescopes needs accurate polar alignments to be able to track longer exposures and also to be able to find the object that you sent to. And of course, like I said, these mounts have different drives, so different transmission systems from motor to the moving parts. And gears are the most commonly used ones, so they are the cheapest ones. Even if these gears are manufactured in a very high end, they always have backlash between each other. So when they are transmitting the movement, from time to time, they will cause something called periodic error. And this will cause tracking error, which we don't want, and which will cause elongated stars. So remember from last week and the previous week, we always want pinpoint stars, round stars, not ellipse stars. To be able to do that, if you don't use an auto-guiding system, which I will explain in a minute, with the mount tracking system, you will not be able to track long exposures like 5 minutes, 10 minutes long exposures without having star trails. For that reason, we use a secondary telescope and a secondary camera other than the main imaging telescope and main imaging camera, and we pick one star, and by using a software called PhD2, we tell that we track this star and say that if this star moves 1 pixel, let's say, or 2 pixels to any direction, this will go and tell the mount that it is going too fast or it is going too slow, and it will tell to adjust the speed so that the stars will not be elongated. It is crucial if we have higher focal lengths, and also if we want to go for 5-minute long exposures or 10-minute long exposures, we have to have accurate auto-guiding system. And cameras, I will again refer to our first class. You can go back and watch it about cameras. There is plenty of information, so I will not repeat those informations. For deep sky astrophotography, of course, you can use a digital single lens reflex or digital single lens mirrorless camera. These cameras can be stock cameras or can be modified. You can buy it. If you remember, I gave some samples. For instance, Canon EOS RA. The A stands for astrophotography. That camera is specifically manufactured for astrophotography and is more sensitive to red light, which comes from hydrogen alpha or emission nebulae. And the other type of camera are called astrophotography dedicated cameras with active cooling system. These can have CMOS sensors. We call them CMOS cameras or CCD cameras. And again, the ones who are curious about what CMOS and what CCD are, they can go back and get some more information from the first class that we had a couple of weeks ago. And for DSLR or DSLM cameras, they're always called OSC or one-shot color cameras. So you cannot buy monochrome DSLR or DSLM camera because, again, in the first class, as explained, these cameras are actually, the sensors are always mono cameras, sensors, but using something called Bayer matrix, they become color cameras. For DSLR and DSLM cameras, they're always one-shot color cameras. But for CMOS and CCD cameras, you can buy mono cameras also that you will have to use filters for specific colors, and I will explain in a minute that you can have red, green, blue, and other filters to be able to capture that color data and then combine them during the post-process. And you will remember we have these cameras. This is actually a DSLR camera. This is a mirrorless camera. This is again a mirrorless camera. This was a stock DSLR. This is manufactured specifically for astrophotography, Canon EOS RA. And this is Nikon Z6 and modified by a third-party company, which is added a cooling system, and also the sensor is modified to be more sensitive to hydrogen alpha light. And we have here CMOS sensors, can be both color or OSC, one-shot color. And we have CCD cameras, again, can be one-shot color or mono cameras. When they are mono, you have 4 filters for visible light. I mean, visible part of the spectrum. They are called LRGB. You know RGB, it's the color actually, red, green, blue. And we have something called L here, which stands for luminance. And you can use filter reels like this, and you mount the filters here. And these are electronic devices that they can change the filter by using some softwares that we will talk about more next week. Using these softwares, you can create sequences, and you can say that shoot, let's say, 50 L and frames. So this filter wheel will change the filter, and it will bring L, and it will shoot 50 frames, and then goes on with the sequence. And for mono cameras, you can also have S2, which stands for sulfur, HA stands for hydrogen alpha, and O3 stands for oxygen 3. So these are different wavelengths of light. You can have those filters, and these are also called narrowband. These are called broadband filters, and these are called narrowband filters. You can create different types of astrophotography with these filters. And for color cameras, you can use light pollution filters. If you are in a light polluted area, some of the light coming from the resources, like human-made resources, like your neighbor's light or the street light, can be cut by light pollution filters. We also have narrow band filters like S2HA O3 filters for mono camera, color cameras that you can actually use to create a different type of astrophotography called narrowband astrophotography. So for cameras, let's remember, like I said, you can go and watch the first class. There was the explanation of these parameters. When we buy a camera, we need a higher quantum efficiency, which is actually the efficiency of the camera, how efficient the photons are used by the sensor. So we need higher quantum efficiency. We need higher dynamic range and higher bit depth if possible, because this will increase the price. And higher full well depth. This was the capacity of each pixels, gathering electron capacity of each pixels. So you can think as pixels as buckets again, and pixels accumulates the electrons. So the number of electrons, if the number of electrons is higher, then that camera has a higher full well depth. So we need that because we want to shoot very faint objects, and we want to collect as many as light as possible. So, and we want lower readout noise. This is also native to camera's inner structure, and camera manufacturers always tries to find ways to manufacture cameras or sensors with lower readout noise. So you have to go and look for cameras with lower readout noise. And of course, a higher delta T, this means how much cooler you can make your camera from the ambient temperature. For instance, let's say if you have 30 degrees delta T camera, that means that you can cool down your camera 30 degrees more. And if you are, let's say, shooting at 20 degrees, that you can cool your camera to minus 10 degrees. Higher this number is better. And of course, you need faster cameras because these cameras have RAMs and other electronic devices inside, processors inside. So we need faster processor and faster connectivity cameras if possible, because this will also increase the price. And yeah, like I said, they need higher RAM and newer RAM technologies and faster process we need. Are we going to buy a DSLR? Are we going to buy a DSLM, CMOS, or CCD, or mono, or one-shot color? This all depends on your budget and on your need. And of course, the sensor size and pixel size, again, depends on your budget and the pixel scale that I will not go through because pixel scale is important. Depending on the focal length that you have to decide the pixel size of your camera. So you have to calculate the pixel size and pixel scale before you purchasing your camera or telescope. Let's say you have camera and you want to purchase a telescope, then you have to know the pixel size of your camera and purchase a telescope which will fit that camera, or vice versa. And we, of course, need computers. You will say that I cannot see a computer here, but you're actually looking at a computer here. This red thing is a computer. This collects the data from the camera, data from the auto-guiding system, data from other stuff, the mount itself, and using Wi-Fi, the information in this computer can be transferred to another computer. By this way, your computer or your cell phone or even your tablet doesn't have to be, you don't have to be just by your telescope. You can be in a warmer place and your telescope can be in colder place outside. You can just communicate with this computer using Wi-Fi, and this computer will do everything. It will create the sequence. It will manage the auto-guiding system. It will manage the go-to system and everything. Of course, this again depends on your budget. These things are quite expensive. You can use just normal laptops or computers to capture the images, or you can use this type of computers, which has different types and different price ranges. And accessories, we of course need cables and always have to have the spare cables. I tend to have at least 2 of each cable, just in case one of them is not usable anymore. And if the weather is clear, not to ruin your night, you have to have at least 2 spare cables other than the one that you are using. And we need dew heaters to avoid dew and icing on your primary mirror or primary lens. We need batteries, or like I said, we need landline electricity. And we need polar alignment tools to have the accurate polar alignment, which is crucial for accurate tracking. We need a power splitter. We need dovetail bars. These bars are the stuff that you will be able to connect your telescope to the mount. You will need headlamps. It's good to have a spare one again, and we will need lots of adapters. And it's good to have again spare ones just in case. And we will have some tools, screwdrivers, other tools, tapes, and everything. And yeah, that is it. I don't know if it was helpful. We will be talking about more in deep space astrophotography. Especially, we will be talking about how we set up the equipment, how and what adjustments have to be done before shooting, and what softwares we use to shoot, and also the other helper softwares during the acquisition of the images. Good evening, good night, good morning, wherever you are.